Hello, everyone. Welcome to Fusion Power, a Mark O'Shea production. Now, if you're anything like me, you're a huge fan of superhero movies. One in particular from 2004 is Spider-Man 2. In Spider-Man 2, Dr. Otto Octavius is attempting what appears to be, based on the reaction of a lot of observers, the world's very first successful nuclear fusion experiment. What some may be unaware of is that this is actually a very real concept and is currently being worked on by Lawrence Livermore National Lab in their National Ignition Facility. There are two primary components to initiating a fusion reaction, and those are fuel and an ignition source, much like many other forms of power generation like coal or natural gas. And we can see in this first image from Spider-Man 2 that it is pure tritium being used. And one thing that they got straight was tritium is a pretty rare isotope of hydrogen, and the earthly supply is fairly limited, but it can be synthesized and it is found naturally produced in space. So a depleted earthly supply does not necessarily mean tritium goes away for good. And deuterium is another isotope of hydrogen that is mixed with tritium for these experiments in Livermore. So the real life applied fusion reaction utilizes a deuterium-tritium mixture. Once fusion is achieved, in either image, we can see the final fused product. They're similar, but the product in Livermore is contained in a vessel that once held the fuel. Now, this looks like a miniaturized version of the sun because, in essence, it is. The sun undergoes many fusion reactions within its core, and they occur constantly. And when the sun releases energy from these reactions, this allows the sun to provide us with our 1400 watts per meter squared of power here on Earth. Now, exactly how does it work? What is happening? This method of fusion is what is called the inertial confinement fusion. And in the initial image from Spider-Man 2, there were only 4 lasers from top and 4 from bottom. We actually have 192 lasers, 96 from the top and 96 from the bottom, to achieve this inertial fusion. And it supplies a pressure of over 10 petapascals, or 100 billion times the atmospheric pressure of Earth. If you've ever taken 2 magnets and tried to make 2 of the same side touch each other, you've tried to overcome Coulombic force, and it is very difficult. Even if you do manage to get them to touch, they're always offset. It requires a lot of pressure and high temperature exceeding 100 million Kelvin in order to overcome the Coulombic force, which is the electromagnetic force repelling the 2 hydrogen nuclei. When enough pressure and enough temperature are applied through all 192 beams, fusion takes place. And we have a chemical equation that makes this reaction possible. We can see that deuterium and tritium are both hydrogen atoms, as they both have 1 proton designated by the 1. And we can see there are different isotopes of hydrogen designated by the 2 and the 3. And these represent the fuel capsule, and the arrow can represent the 192 lasers, and the product side consisting of helium with 4 neutrons and 2 protons as supplied by the 2 hydrogens. But why wouldn't it be helium with 5 neutrons? Well, looking at it, helium-5 does exist, but it has a very short half-life, and it makes it almost negligible. So we just say 4 helium plus 1 neutron. Another way of thinking about this is helium-4 is so happy to be itself that it just immediately rejects the neutron and tells it to leave. And the breaking of the bonds that hold together these 2 hydrogen isotopes and the reassembly to helium and rejection of the 1 neutron provides us with almost 17.6 mega electron volts of energy. And a final note comparing the real life fusion power project to the cinematic fusion power project is that this fusion project produces a short burst of energy as opposed to a self-sustaining miniature sun. Self-sustaining with more energy generation than input is the goal, but we're not quite there yet. And here I have a works cited one image of the sun. Thank you all for listening.